throwing guesses at it until it gets to something that feels is close enough, or you feel is close enough, depending on how much control you have over the program. That's how you solve these equations. Now, if you apply restraints to the problem, so this is a general solution where we can have these be whatever we want within the plane. M1, M2 can be whatever we want, U1 and U2 can be whatever we want. General solution. All right? But if we remove some of this freedom, we say, no, we're going to restrict some of this stuff, then you can get to an analytic solution. Okay? And we're going to do one. Okay? So has everybody written these equations down? All right? So I'm not going to expect you to solve these analytically. It's not possible. At least not by me. Maybe there's somebody super clever who could do it, but I don't think so. Normally with systems of nonlinear equations, you can't solve them analytically. It's going to be bad. But as I said, if we add enough constraints to it here, if we limit it enough, we can solve it. So that's what I'm going to do. And I'm going to do the one that we did in the billiard ball lab, where we had the two billiard balls, the cue ball, and the object ball. That first collision, we can solve that. And we can get an answer. And interestingly, we'll find the computer answer, the SOLIDWORKS answer, is wrong. It's not very wrong. It's pretty darn close. But it's not actually dead on the money. And we, because we're doing an analytic solution, we get a dead on the money answer. Like I said, with this numerical technique, it gets to within a certain error bound, and it says good enough. It calls it quits. Okay? And so you can end up with you're a little off. You're a little off. Whereas an analytic solution, it's precisely that. Okay, there's no error at all. I mean, given your assumption, like there's no friction, no error resistance, it's a plane, it's perfect cross contact. But given all your assumptions, it comes in with dead on the money answer. So if we have the special case where M1 equals M2, that's our first constraint. Okay? We've limited. These aren't free anymore. They're the same mass. We're also going to say that one of the balls, and I'm just going to pick this U2. It could be either one, but I'm just going to pick this U2. U2 equals 0. Just to say it's not moving. Okay? So this is the object ball. U2 is the velocity of the object ball. We're saying it's not moving, just like in our SOLIDWORKS ball. Yeah.
On the final, are you using
Potentially, but we'll see. There's a way. We'll see how things go over the rest of today and on Monday. We'll see. I think on the homework. But it won't be this complex. I said this one you can't solve. I'm not going to expect you to use a numerical solver. I'm not going to give you the general case. It will be a limited case. It may not be quite as limited as the problem I'm going to do right now, but it will be a limited case. So, here we go. All right. So, we have M1 equals M2, and we are still having billiard balls. It is still the last collision. So this is the restriction we're putting on it. Is this right here. We're saying that, they weigh the same, and we're saying that one's not moving. All right? So what we have here is we have our two balls, and I can have them, here's the one ball coming in. This is U1. So this can still be however we want it to be. And here it is, the ball. And I have this other ball. I don't know. Say here. Okay. I have the line of contact. Say there. I have my theta like this.
Oh my God.
Solvable. This is solvable. Here's something you can do to make it easier, is you can redefine U1 as being in the y direction, or we can set up a reference frame however we want. So I'm going to I heard that.
That's low. That's low.
I heard that. So we can put our reference frame oriented however we want. And so it makes our lives easier. I'm going to say that all of U1's direction is in the y direction. So I can set up my reference frame. I can say what I want. I can say y is that way. X is that way. There's no reason why not. I mean, this on the board and the board happens to be up that way, I can redo this, so I'm going to. So I have it like this, where I have U1 headed up this way, purely in the y direction. I have the other ball over here. I have my line of contact like that. This is CG's here. Okay? And so now I can develop some equations to be able to solve this. Yeah. So we have U1 coming in right here. U1. And then the force that it's going to apply, this is stationary. And so as before, we're going to apply a force along the line of action to the second ball. It wasn't moving. We're applying a force in that direction. So what direction is it going to move post-collision? That way, according to the line of action. So our V2, so this is ball 1 here. This is number 1. This one over here is number 2. So V2 is going to be heading off in this direction. V2 is going to be heading off that way. Okay? For our conservation momentum and our conservation of, basically our conservation momentum in the x and the y, this guy's going to head off this way. And it's also conservation of energy. If I redraw this, I think I will, the vectors reposition. Still the same thing. But I'm going to draw U1 like this. That's U1. I can position it however I want. It's both going the same way. I'm going to reposition V2 like so. Still going the same way. Okay. And
Tail on the U.
put the tail on U. U1. Happy?
Yeah.
Okay. And so our V2 is going to be like that. Or V1 rather. And our angle theta is this guy right here. And so we know U1, and we know theta, and so it shouldn't be too surprising if we come up with V2 and V1. So we can set it up like this. For this limited case, where U2 isn't moving and M1 equals V2, this is one of the vectors in there. These are the velocity vectors. And the reason why this is true, I just want to explain why this diagram is true. We're going to take all of our equations are coming off this right here, just with a trick. Alright? And so what this is showing us is that, first of all, kinetic energy needs to be maintained. So what is kinetic energy? It's the square of the velocities. Okay? So the kinetic energy coming in, and where the masses are all constants, you can just leave the masses out of it. Divide by 2 and just ignore that. All we care about is the velocities. Right? And so our velocity coming in is U1 squared. Our energy, rather, coming in. Our energy coming in, kinetic energy coming in is U1 squared. Are we following me on that? Our velocity afterward is mu V2 squared plus V1 squared. Right? So what's the Pythagorean theorem? V1 squared plus V2 squared equals U1 squared. So because we've set this up here with this being a right triangle, this shows the kinetic energy has been conserved. Okay? conservation of momentum in the x is conserved. So our momentum in the x is nothing coming in. U1 is going straight up. There is no movement in the x, so the momentum in the x is nothing. And so what that means is the velocity of the one ball in the x times its mass plus the velocity of the other ball in the x times its mass needs to equal 0. This is just like I'm going to do the sum momentum in the x for that billiard ball deal. Okay? So what's the x component of V2? It's this distance right there. And it's positive. Okay? So that's V2x. What's V1x? It's this guy right here, the exact same thing. V1x, except it's negative. So when we add V2x to V1x, we get 0. So momentum in the x has been conserved. What about momentum in the y? Well, our momentum in the y is basically U1. Again, the masses are constant, so the masses can drop out. So we need to have the velocity pre-collision in the y equal the sum of the velocities post-collision. Again, we have this right here is our chunk of this distance here is V2 sub y, right there. And then this distance right here is V1 sub y. So, as they should, V2 sub y plus V1 sub y equals U1. So we managed to get all three of those constraints, the conservation of momentum in the x, conservation of momentum in the y, and conservation of kinetic energy in one diagram, one handy-dandy diagram that we can solve. If we know U1 and we know theta, I would hope that all of you would be able to do the trick to figure out what these guys are. We know it's a right angle. And